also talk about symmetries with figures. So mathematically, a geometric figure has a line of symmetry if it is its own image under a reflection in the line L. So if we look at figure A, we actually have 3 different lines of symmetry that we can reflect over. B has a single line of symmetry in the horizontal. The star in this quilt has 8 lines of symmetry, and this boat has a vertical line of symmetry. So how many lines of symmetry does each of these drawings have? The first hexagon will have 6 lines of symmetry, one that goes through each opposite pair of vertices, and another that will go through opposite sides at their midpoints. So that gives us a total of 6 lines of symmetry. This A should have a single line of symmetry through the vertical. This oval C will have a line of symmetry over the vertical and the horizontal, so 2 lines of symmetry. And Z will actually not have any lines of symmetry. We can't go vertical or horizontal or diagonal or any way. This is not a symmetric figure with itself. We can also talk about rotational symmetry. So a figure has rotational symmetry or turn symmetry when the traced figure can be rotated less than 360 degrees about some point. The turn center, so it matches the original figure. So an equilateral triangle has rotational symmetry of 120 degrees. If I take the center of the triangle and I map point A to point B, B to C, C to A, and it maps onto itself. I could also take this kind of leaf and do the same rotation of 120 degrees. So we can determine the amount of turn for the rotational figure symmetries of these figures. This is a pentagon with some interior split ups into triangles. So we're going to need to take 360 degrees and split it into 5 equal parts. So we can use 360 divided by 5 is 72. So I could move 72 degrees, I could move 144 degrees, I could move 216 degrees, I could move 288 degrees, and those will all give me rotational symmetry. Now for B, I have 1, 2, 3, 4, 5, 6. This is a hexagon with triangles on the outside. So I'll take 360 degrees and divide by 6 and get 60 degree angles from the interior center. So I will move this point 60 degrees. I could move it 120 degrees, 180 degrees, 240 degrees, or 300 degrees. Finally, this figure, I need to rotate a full 180 degrees for it to be back on top of itself. Any figure that has rotational symmetry of 180 degrees is said to have point symmetry around the turn center. So since I can take my star here and map the top 180 degrees to the bottom and it's symmetric, then this has point symmetry. The circle has point symmetry. The hexagon I can use point symmetry on, and this is Z, I can rotate 180 degrees, so it has point symmetry. We can also classify figures by their symmetries. So geometric figures in a plane can all be classified according to the number of symmetries they have. We can use lines of symmetries and turn symmetries to define various types of quadrilaterals normally used in geometry. So let's think about a triangle that's described as having exactly 1 line of symmetry and no turn symmetries. What would that triangle need to look like? If I have 1 line of symmetry, then my triangle is going to need to have 1 vertex on my line of symmetry, and the 2 sides will need to mirror each other along the reflection line. And I need it to not have any turn symmetry. So that means that the distance between the two endpoints needs to be different. So this needs to be an isosceles triangle because I don't want my third side to be congruent, or else it will have turn symmetries. So here's another example of what this triangle could look like. And that is all I have for you today, so I hope that this has been helpful, and please be in touch if you have any questions, and have a great day. Bye.